Light is a particle. Here are all the variables that you need to know. Propagation speed. While the individual points along the wave move up and down, the overall progress or propagation of the wave goes left to right. And it does so at 2.998 times 10 to the 8 meters per second, the speed of light. Why are we talking about light as a wave when this is a video about light as a particle? And that's a great question. But light actually exhibits both forms, wave and particle, and we need to use each model to understand the other completely. Frequency is also something to understand by referencing the wave model. It's defined as the number of cycles or repetitions that the wave completes in a fixed amount of time. So we calculate it by dividing the number of cycles completed by the amount of time it took to complete those cycles. Next up, we have energy. And essentially what that is the ability to do work and make things happen. Now that might sound super vague what I just said, but the way that we use energy is incredibly understandable. Energy is one of the most defining features of the particle model of light, as we often describe light particles as pockets of energy, which we call photons. In other words, whenever we see the word photons, we automatically know that we are dealing with light as a particle. Energy of a particle is quantified using this equation. Energy of the photon equals h times frequency of the photon, which brings us to Planck's constant, which is a constant. It's the exact same thing every time. It's quite devoid of concept, and it's equal to 6.626 times 10 to the negative 34 joule seconds. It's there to make the units all cancel out. Wavelength is the horizontal distance it takes for a wave to repeat itself. It could be peak to peak, it could be trough to trough, it could be anything as long as the points are consecutive with the same height and the same slope. Starting with wavelength is a means to an end to figure out what corresponding energy of the photon that we have. Work function is a term that we use to describe energy in a very specific context. It's the minimum amount of energy a photon must have in order to eject an electron that's the outermost in an atom. We have to overcome the energy that's associated with the bond that the electron has with the atom. The energy of the photon is absorbed by the electron, and any leftover energy is in the form of kinetic energy. Power, on the other hand, is the rate at which energy is transferred, meaning gained or lost, per unit of time. For this reason, we often write it as change in energy over change in time. Likewise, we have units of joule per second, and that is also equal to a watt. Momentum. We also have momentum, which is a particle quantity that characterizes that particle's motion. There are two different equations that we have to describe momentum depending on if we have light or if we don't have light. Light is very unique. Usually we have something that has mass, and we have mass times velocity as a way to calculate momentum. But light has momentum. There's different experiments that prove that it has momentum, but yet light doesn't have any mass. And it just happens to be equal to the energy divided by propagation speed. The good news is that we use the same units, no matter if we're talking about something that has mass or something that doesn't have mass, light.